Let's continue to talk about thermochemistry. And as we were seeing in the last PowerPoint, the first law of thermodynamics tells us that any change in internal energy can be seen as an exchange of heat and an exchange of work. And the work can be calculated as the product between the pressure and the change in volume, with a minus sign that we need in order for the sign of the work to be consistent with the convention that we have decided to adopt. So let's imagine that we are operating a constant volume, as it would happen in a bomb calorimeter. The bomb calorimeter is sealed and it has rigid walls, so it could resist increases in pressure without changing volume. If the volume is constant, delta V is going to be 0. Therefore, whatever is the pressure value at any given point, the multiplication will give you 0. So there is no work. All the internal energy is a change results in heat being exchanged. So that will be a good way to measure the variation of internal energy. However, if you consider most of the reaction that you've been doing in the lab, they happen in an open container. Is the pressure that's going to be constant, not the volume. If there is a gas, that gas formed in the reaction, that gas can expand. But the pressure is always going to be constant and is equal to the value of the pressure in the room. That's the barometric pressure. It can be measured through a barometer. So here is a coffee cup calorimeter, and as we said, in this condition we have constant pressure. Therefore, the calculation of the work becomes relatively simple, because all we have to do is multiply the pressure by the change in volume and then use the minus sign in front of it. And this, as I was saying, is relatively simple because pressure is constant. If the pressure would be changing over time, then it, from the mathematical point of view, you would require more complicated tools and you would have to use calc. So the heat exchange at constant pressure takes a special name, that is delta H. So we define a new function of state, H, and that's called enthalpy. And the variation of enthalpy corresponds to the heat exchange at constant pressure. So we can rewrite the first law of thermodynamics consequently. And you can see how H is a function of state, because everything else in that equation is a function of state, U and V, or is a constant like P. So enthalpy can give us a sense of the amount of energy stored into the reactants and the products. When the delta H is positive, as it happens on the right side of the picture, it means that during the reaction, the material is going to transform into something that has more energy. So you see that the products are drawn higher than the reactants, and the difference in energy is the energy absorbed by the reactants. In an exothermic reaction, instead, the products are going to have less energy than the reactants, so there is a loss of energy. This energy is going into the surrounding, and therefore the reaction is exothermic. Now, this kind of diagram that you probably saw in your first semester chemistry seems to imply that the transition between reactants and products follows a direct path, like a linear path, a simple path. That's not the case, as you've learned by studying kinetics. There is actually a little bit more complicated path. The transition from, in this case, we are representing the combustion of glucose to carbon dioxide and water. And you can see that the transition is not direct, but before being able to get to the final products, we need to go through a state that's called the activated complex that has more energy than both reactant and products. So there is this initial demand of energy that's called the activation energy that's necessary for the reaction to happen. It's a bit like an object being on a shelf. If falling down would be a spontaneous process, but before you manage to falling down and release that potential energy, you need to push the object onto the edge, and that would be the correspondent of the activation energy. You might remember during the first semester of chemistry, you've been doing some experiment with the coffee cup calorimeter. So in calorimetry, we measure the amount of heat that is given off or absorbed by a substance. And the specific heat is the amount of heat that is required to raise the temperature of 1 gram of a certain substance by 1 Celsius. So you see a table here with several specific heats. And the first one is aluminum, that has a value of almost 1. You see other metals, they have quite different values. They tend to be smaller. In particular, there is a inverse proportionality between the atomic mass and the specific heat. The higher is the atomic mass, the lower is the specific heat. And that you see for gold and mercury, you have a pretty small value, and aluminum, that's the lightest, basically, has the highest value. So this is, in a nutshell, the rule of Dulong Petit that you used in Gen Chem 1 with the calorimeter experiment. But water definitely has a higher value than everything else. It's almost 4 times the value of aluminum. So what's the consequence of this? So how can we measure the amount of heat given off or absorbed by a certain amount of substance? We can use the calorimetry equation. The calorimetry equation tells us that the heat exchanged is going to be proportional to how much material we have, to how big is the difference in temperature that's going to be achieved, and the proportionality constant is the specific heat, C. So the change in temperature is always measured as final minus initial. In this table, you see the unit is Celsius, but it doesn't really matter to use Celsius or Kelvin, because in this type of calculation, you're always calculating the difference between the temperature. And that is exactly the same number, regardless if you're using Celsius or Kelvin, because the size of the degree in both scales is the same. What's different between the two scales is simply an offset. So let's imagine we have 100 grams of aluminum, and the initial temperature is 80 Celsius and is dropping down to 30 Celsius. How much heat would that aluminum given off in that process? We can do the math. You need to remember that the initial temperature is 50. You always go initial minus final. So that means that the change in temperature is going to have a negative value. The delta T is really the only thing with a sign in that expression, because specific heat and mass are always positive. So because of that, in this process of cooling the aluminum, we're going to calculate a negative value of Q. That makes sense, because the aluminum is the system, is losing heat, so the value of the exchange of heat should be negative. What would be the difference if we would do the math with water? The only different number would be the specific heat, 4.184 as opposed to 0.9, and this gives a much larger value of joules, 12.6 kilojoules. So the implication is that water, it's good for storing heat. That's why it's used as either refrigerant liquid or a heating liquid, for example, in certain type of house heating systems. This is the coffee cup calorimeter that you've been using in your first semester chemistry lab. It's made of two styrofoam cups nested into each other to improve the insulation. The fact that this is an isolated system is still sort of an approximation, so we really need to try to work fast. Otherwise, if it takes too much time, we cannot ignore that there is a certain loss of heat towards the surrounding. But as long as we are fast, we can assume that this is an isolated system. It's not sealed, so the system is at constant pressure. at any given time during the experiment, the pressure inside the calorimeter can equilibrate with the pressure outside, that is the barometric pressure. So because it's an isolated system, we can say that whatever heat is given off by a reaction or by a hot body is simply and completely going into an increase, producing an increase in the temperature of the water inside the calorimeter. To be perfectly correct, we should also consider that some of the heat will increase the temperature, not just of the water, but also of the internal walls of the calorimeter, the stirrer, the thermometer. That's quite a small number, so as long as, for example, our reaction is giving off a lot of heat, we can kind of ignore that component and simplify and say that the heat absorbed by the water is plus the heat given off by the reaction put together give us a zero. That means that if we calculate the heat absorbed by the water, the heat given off by a certain reaction is going to be the same number, just with a different sign. The heat absorbed by the water can be calculated easily because we know the specific heat of water. We can measure with a thermometer the change in temperature, and we can use a scale to determine the mass of the water initially put in the calorimeter. And this allows us to calculate the heat of reaction. Let's see an example. In this case, we are trying to determine the molar heat of solution. When we dissolve sodium hydroxide in water, that's a strongly exothermic reaction. So we have 41 grams of sodium dissolved in 100 milliliters of water. The initial temperature of the water is 19.5. The final temperature of everything, because once the reaction is done, all the calorimeter, thermometer, stirrer, water will all have the same temperature of 31.7. So the starting point is the fact that the calorimeter is an isolated system. So the heat of solution plus the heat absorbed by the water is going to be zero. Therefore, we can calculate the heat of solution as equal to the heat absorbed by the water with a minus sign. The heat absorbed by the water can be calculated with the calorimeter equation. So we have 4.51 grams. The specific heat of water is as usual 4.18, and then we need to go final temperature of 31.7 minus initial. So in this case, the change in temperature is positive. That will make the heat absorbed by the water positive, as it should be, because for the water is an increase of energy. Therefore, using the proper sig fig and transforming into kilojoules, we get 5.10 kilojoules. So the heat given off by the solution is going to be minus 5.10 kilojoules. That makes sense because that's an exothermic reaction. So from a perspective of sodium hydroxide, it's losing energy. The system is losing energy. Now we need to be careful because what they're asking us is the molar heat of solution. So we need to figure out how much heat is given off by 1 mole of sodium. We do not have 1 mole of sodium hydroxide. We have 4.51 mole grams of sodium hydroxide. So we need to set up a series of conversion factors. So we know that 5.1 kilojoules are given off by this amount of sodium hydroxide. So we divide, then we multiply by the molar mass of sodium hydroxide. So we can simplify grams of sodium hydroxide, and we get the kilojoules per mole. That's what we're looking for. That is 45.3 kilojoules per mole. There are situations where we cannot perform a reaction in a calorimeter, or we don't have a lab, and all we have is paper and pencil. In which case, we can do the math by calculate the theoretical value of the heat given off by the reaction by using Hess's law. Hess's law is based on the fact that enthalpy is a function of state. Therefore, the actual value of delta H for a certain reaction does not depend on the path we take to go from reactants to products, but only from the initial and the final state. So as long as the products and the reactants are the same, it doesn't matter how we get there. So for example, the main reaction that we are interested in is a reaction that converts A into B. And in an ideal world, we would like to be able to perform that in a calorimeter. But if that's not possible, we can put together a fictional path that could be made of 2 or 3 or 4 or as many steps as we need. And that's a sort of a thought experiment, something we are not actually to do. We are just only going to do the theory, the reasoning, and the calculation about it. As long as the initial and the final points, so A and B, are the same, the result of the calculation is going to be the same. So let's see an example. We want to know the enthalpy involved in burning methane. Now, that's a reaction that can be done, but let's say we don't have a lab, and as I said, all we have is paper and pencil. Due to a lot of experiment that's been done in the 40s and in the 50s, the literature has plenty of information about all sorts of reaction. So if you go to the end of your book, you can find a lot of delta H of reaction. And so what you have to do is try to put together an alternate path. For example, you could think of burning methane and oxygen to carbon monoxide and water, and then proceed further to CO2 and water. So the sum of the enthalpy involved in those two steps would be equal to the value we are looking for. In this way, we can calculate that the enthalpy of the reaction is negative 890 kilojoules. That makes sense because burning stuff is typically an exothermic process, right? So we are looking for a negative value. A thermochemical equation is an equation that includes the amount of heat exchanged in terms of enthalpy. So for example, in this case, we see that we have water in the solid state, so ice, it's melting into liquid water, and the coefficient R1 for both reagent and product. So that means that to melt 1 mole of water, that is 18 grams, is going to take us about 6 kilojoules. It's positive because it's endothermic. To melt ice, you need to provide heat. And so those 6 kilojoules per mole should be treated as a reagent or a product, in this case being endothermic is a reagent, in the sense that you can do math with the same way you would do when you were doing stoichiometry. So for example, if I reverse the reaction, so if my reaction consists into solidifying water, so to transform 1 mole of liquid water into ice, I would have to subtract it. So that would be an exothermic process, but that would be the very same amount, just with a minus sign. If I increase the amount of water, for example, if I have 2 moles of water, 36 grams, then the amount of energy involved would also be twice as big. Let's see an example of a stoichiometric calculation using delta H. So this reaction is the decomposition of sodium hydrogen sulfate, and this is an exothermic reaction that gives off 231.3 kilojoules per 2 moles of sodium hydrogen sulfate. We want to know how much heat is given off if we have 3.60 grams of hydrogen sulfate. And we are also given the molar mass. Now we can do an eyeballing, an expectation of what we should get. We have 3.6 grams. If we would have 360, that would be exactly 3 times the molar mass. So we know we would have 3 moles. we have 100 times less, so we have 0.03 moles. So this number should be divided by 100 times 3, so we should get about 6.9, something like that, kilojoules, if it makes sense. So let's proceed and put together our convection factor. So the first conversion factor is based on the fact that 231 kilojoules are given off by 2 moles. I want to put the kilojoules on top because I know that my final result should be kilojoules. That's what they're asking me, how much heat is released. Then I want to convert moles into grams because I'm given the amount of grams of sodium hydrogen sulfate. So I'm going to use the molar mass. I'm going to put, and this is my second conversion factor, I'm going to put 1 mole on top because I want to simplify with these moles, and I want to put therefore the grams at the bottom. Finally, I'm going to use the amount of grams that are given for this reaction. So this way I can simplify and I get moles are going away, so this divided that is going to be the kilojoules per 1 gram, and then I multiply by the grams that I have, so this is going to be that, and I get the amount of kilojoules per this reaction. So there are special values of enthalpy, enthalpies that we call standard, and these are the enthalpies that are recorded with a particular set of parameters like pressure, temperature, and concentration. So that we define as standard state. So the standard state is the condition where we have the substance is pure and we have a temperature of 25 Celsius. Now, if you remember the standard state for gases, the temperature was 0 Celsius. So why do we create confusion by using a different temperature in thermodynamic? Because enthalpies are determined by through experiments, like the one we've seen with the calorimeter, and it's just more comfortable to perform those experiments at 25 Celsius. That's a typical room temperature, albeit a little bit warmer than I would personally define room temperature, but and it would be extremely uncomfortable to do all those experiments at 0 Celsius, basically. The substance should be present in its most stable form. So, for example, for water, the most stable form at 25 Celsius is liquid, not ice. For, let's say, ozone and oxygen, oxygen is the most stable form of the element. So, if we have allotrope, you need to pick the most stable of the allotropes. If we have a solution, the concentration should be 1 molar. That's kind of a relatively high concentration. And if you have a gas, the pressure should be 1 atmosphere, and the behavior of the gas should be ideal, so no repulsion, no attraction, the volume of the particle should be negligible with respect to the volume of the container. In the proper unit system, atmosphere are not the standard units for pressure, but chemists are creature of habits and they keep sticking to atmosphere. There are particular reactions that are interesting, and those are called formation reaction. So as you notice, there is the symbol, the degree symbol is used to indicate standard, and then there is a subscript in this case for reaction. So this is a generic reaction, while this means a very specific type of reaction, formation reaction. So the formation reaction is the reaction where you are combining the elements to form 1 mole, so this is important, of the compound in standard condition. And they are listed for every substance that you can think about. There is a list containing all the delta H of formation of any compound, and you can find it at the end of your book. So you see, for example, here you can see the reaction of formation for methane. So the two elements would be carbon and hydrogen. We have to write the reaction so that we are forming 1 mole of methane, so there should be a coefficient of 1 here. Otherwise we have to modify the coefficient so that the coefficient is 1. And we are using graphite and not diamond because graphite is the most stable allotrope of carbon at 1 if the pressure is 1 atmosphere and the temperature is 25 Celsius. When you write a standard formation reaction, the reagents should be only elements. The product should be 1 mole of the compound. So for example, if I write for the reaction formation for water is made of oxygen and hydrogen, right? So I write this, then I try to balance it and I write that. But that doesn't work because I have 2 moles of water and I need to write this so it's 1 mole of water. So the solution is to modify the coefficient without changing the relative ratio. So I need to, for example, divide everything by the same number or multiply everything by the same number. So I'm going to divide everything by 2. Because I cannot divide a molecule of oxygen in 2 because it's a B-atomic molecule, if I write a isolated atom of oxygen, a radical, that would be unstable, so that's not the most stable form for the element oxygen. So I have to use a fractionary coefficient. That would be this. So this is a table with some values, and I just want you to notice some patterns. So first of all, there is a net prevalence of negative values. So that means that the reaction of formation for a lot of compounds, for the majority of the compounds, tend to be exothermic. Then you see that there are a bunch of zeros. So if you notice, all those zeros are elements in their most stable state. So for bromine is going to be a liquid, for aluminum is going to be a solid, for carbon here is going to be graphite. Diamond does not have a zero value. The same happens for oxygen, where I have the stable form, O2, and I have ozone, that's the non-stable form, so it's different from 0. For hydrogen is another interesting thing. The element is 0, but hydrogen as an isolated atom is not the most stable form, so it has quite a high value. So it then tells me that if I want to separate 2 atoms of hydrogen in a B-atomic molecule, I need to spend 218 calories. So I think I'm going to go for a retirement scheme here, and this is my idea. My idea is that I'm going around campus, picking up all the pencils that students are leaving behind. And I'm going to take out all the leads that, as you know, are not made of lead, but are made of graphite. And so I'm taking all that carbon in graphite form, and I'm going to, that's coming for free, so there is no cost in this part of my operation. And then I'm going to transform it into diamonds. And then I'm going to sell them. I'm going to make a lot of money so I can retire early, especially now that the stock market is in a pretty bad shape. So I will give you 10 points of extra credit if you can explain neatly and clearly why this plan is going to work or why it's not going to work. So 10 points of extra credit for this. I will put in Canvas folder to upload the answer. So we have already discussed this part, so we are good. Now, why do elements have a 0 value of enthalpy? The problem is I'm not, for the same reason, I cannot measure the absolute value of U, internal energy. I'm also not able to measure the absolute value of the enthalpy. There are just too many components into it. I can only measure changes. So that forced me to take a baseline somewhere, and this choice is going to be somehow arbitrary. So it's a bit like measuring the elevation of a place. The elevation, the absolute elevation would be the distance from between that place and the center of the Earth. but no one is going to be able to measure that. So we can measure how much higher is this place respect to a reference point, and what we pick is sea level. So we can say, for example, that the elevation of Platteville is 988 feet, because it's 988 feet higher than the sea level, and we put the sea level to 0, but that's sort of an arbitrary decision. For example, my hometown is minus 11 feet respect to the sea level. That creates some inconveniences, but we deal with that. So our arbitrary reference point are the elements. We set all the elements to 0. In this problem, we have to apply the Hess's law to calculate the delta H of a reaction relative to the combustion of benzene, given the delta H information of the compound involved. So in a typical problem, you would be given the reaction already balanced. So from this reaction, we say that there are 2 reactants, benzene and oxygen, and 2 products, CO2 and water. You are given only 3 values of delta H of formation: benzene, CO2, and water. You're missing oxygen. The reason you're missing oxygen is because this is an element in its standard state, so the delta H of formation is by definition 0. They would never give you that information explicitly. They would just not give you the delta H of formation for oxygen. So you need to remember that by yourself, that that's going to be 0. So to calculate the delta H of the reaction, we need to take the delta H of formation of each of the product, multiply by the coefficient in front of the product formula in the balanced equation, and then take the delta H of formation of the reagents, multiply by its coefficient, and change that sign. So this is the formula that we're going to use. So we are taking the delta H of formation of CO2 multiplied by 12 plus the delta H of formation of water multiplied by 6 minus the delta H of formation of benzene multiplied by 2. And this gives us a quite big negative number that makes sense because we know that burning is exothermic. You may think that you're done, and if this is a multiple choice, chances are that this would be given as one of the potential answers. But you're not done, because what they're asking you is how much it is released per 1 mole of benzene. But in this reaction, you have a coefficient of 2 in front of the benzene. So you are releasing 6,500 kilojoules when you're burning 2 moles of benzene. To find the amount released per 1 mole, you need to divide by 2. Another common type of problem is a problem in which you are asked to combine a set of reactions in order to obtain a target reaction. So the target reaction is this, and you need to combine the 3 reactions here in order to obtain this one. Now you need to trust the teacher that there is a solution, and then typically, unless it is explicitly said otherwise, you have to use all 3 reactions. So it may be a process of trials and errors, and if you get into a dead end, just throw away everything and start again from scratch. But a good strategy is to take pick one substance at a time. So let's say graphite, okay? So I'm going to look into the 3 reactions and see if there is one in which graphite is present. And I see that graphite is here. So it's on the correct side, because I wanted the reagent and there's a reagent here. It's also in the correct amount, that is 1 mole. So I'm lucky, and I just copy down that reaction. Because I didn't do any modification, I don't have to change the value of delta H. Then I'm going to look for sulfur in its rhombic form, that's this form that's stable at in standard condition, and sulfur can be found in the reaction labeled as B it's on the correct side, but I don't have enough. I have half of how much I would need. So, but I can do, I'm free to do modification to this reaction, as long as I do the same to everything. So, for example, I could multiply by 2. If I multiply by 2, I get 2 in front of S, 2 in front of oxygen, 2 in front of SO2, but I also have to multiply by 2 this number. So, I can do that. And then finally, I'm looking for CS2, and I want it on the product side. So I see it in C, correct amount, 1 mole, but wrong position. So I need to flip that reaction. That's another thing that I can do. I can flip reaction left and right, in which case I would have to change the sign of the reaction. So I can flip it and do write down the number. Now, before I do the math with the enthalpy, because the enthalpy of the total reaction is going to be the algebraical sum of these values. Let's first check that by composing these 3 reactions together, by merging these 3 reactions together, I actually get the reaction that I was looking for. So it's a bit like algebra. You sum everything that's on this side of the arrow, and you write it here, and then you sum up everything that's on the other side of the arrow and you write it down here. And you can simplify things that appear on both sides, like if you're doing algebra. So here I have 1 oxygen plus 2 oxygen is 3, and I have 3 oxygen on the other side, so it cancels out. And then I have 1 CO2 and 1 CO2, and that cancels out as well. And then I have 2 SO2 and 2 SO2, and that cancels out. So all is left is graphite, 2 sulfur, giving me 1 CS2, carbon sulfide. That's exactly what I was looking for. So now that I know that everything is working, I can do the math with the enthalpy and getting the total enthalpy. So you need to identify which equation you're asked to do the calculation for, and consider the coefficient, what are the reagents, what are the products. Manipulate the set of equations that I'm giving you so that each substance appears with the correct coefficient on the correct side of the equation. You have to do the same manipulation to delta H. So if you are flipping reagent and products, you need to change the sign. If you're multiplying or dividing, you need to multiply or divide the value of delta H. Then you add everything together. You simplify to check that you get the reaction you were interested in, and then finally do the math with the values of delta H. You should assume that you have to use all the equation provided unless there is an explicit different instruction, and then there is a solution.